Hello and welcome to day 13 of the Advent of Code 2021. My name is Jacob and I will walk you through the solution that I came up with in Kotlin today right now. If you already know this puzzle of today, please use the chapters below to skip ahead straight to the solution. Otherwise, I'll quickly explain, I won't read this, but quickly explain what the task of today's puzzle is. Otherwise, the following video will probably be a bit boring to watch if you don't know it yet. So today we're doing, as it says here, origami in essence. So the setup is that you have to imagine we have some transparent paper. So this kind of like plastic cellophane paper that you would put on like a projector, an old school one to write on. And we're given, essentially it has a grid marked on it. And we're given coordinates on the grid that contain like a marking, a dot or a cross or something. Which is precisely our input right here. And now all in head quotes we have to do is simulate that this paper is folded over either along the Y or the X axis of this grid at this index on the axis. And we do this repeatedly. You see we have a few instructions, in this case only two, such that points after the folding, so you have to imagine this a bit visually, after the folding points will overlap, or might, I have to say, might overlap, such that over time you get like some picture that forms. So if we imagine this is the input from above here, so this is how we start. The hash signs here, the pounds are a marking, and the dots are like empty spaces. So if we fold it on the Y index 7, so this dotted line or hyphenated line or whatever, we always fold from bottom to top and from right to left. So we would fold this part on top of this part, such that you arrive with half the grid in terms of the tallness, the height or whatever. On the y-axis, and now some things overlap. You see here that everything that matches the position right here after the folding will now overlap. So if we fold it again in the middle here on the number 5 index on the x-axis this time, so we fold this side onto the left, and we actually arrive with this nice square. So you see things where there was like nothing here had something here, so now it will overlap and there's something there now, and vice versa. There was nothing on the side that we fold onto, but there is something that matches that right here in this case. Sorry, I described that matches something right here and right here, for instance, such that we arrive at this nice square at the end. Right, so the goal now is, for the first part, we have to count how many markings, dots, will there be visible only after we executed the first fold instruction. So in the example, this one right here. So let's jump into the code and take a look at just that. Obviously, first things first, we parse our input. For this, let's check that we return coordinates, which makes sense what that is in this case, and a fold instruction class that I created, show you in a second. So to parse the input, obviously we split by a double new line character, such that we get like the top part here with the coordinates and the bottom part with the instructions. So the only part where there's two new lines after another is this one here and then another one there. So we split it nicely along that. So now we have all the coordinates and all the instructions. We split the coordinates again by new lines, and then each of the lines by a comma, such that we have the x and y coordinates. We again use here the structuring declarations, just as we did here already, to get the x and y, and then we simply create a coordinates object. I'll also show you in a second, that I already used in a previous day to simply hold x and y coordinates. So now we just simply have all the coordinates in a list. For the instructions, we obviously also split by a multi-line, and then we split by this fold along right here, such that we would get everything that's after there. Then we split by equality sign such that we get x and the value. So axis, I called it x or y, and the value. Then we create this fold instruction. There's an axis in this, so let's take a look actually at fold instruction. X or y, it's an enum, because I figured, yeah, that's a good use for an enum. So we simply say, give me the uppercase of this exit and then the value, axis value of. And of course, the value that we actually fold, the index, so to say, is the second part. So a fold instruction, as you already mentioned, is simply a reference to an axis and at which index, I could have also called it index, I guess, we do actually the folding. Right. Let's quickly look at the coordinates, such that we also has that. Not much to see though, it's just this. At the end, we return a pair of coordinates and instructions for the simple reason, honestly, that here again I can destructure. So now we have two variables with coordinates and instructions right here. Now comes the interesting part. Let's ignore this line right now and instead look at the grid. I explained this in way more depth in, I believe day 9 is where I first introduced it, but of course we will look quickly at which parts of it we reuse for today's puzzle. So we give it all of the coordinate values, and here it becomes a bit confusing, as well as a default cell value, which we have right here. So the way that I designed this right here, and this is the only information you really need, is that you have a grid, which is generic, so it can hold any, like the cells themselves can hold any generic value. Same obviously then the cell is also generic. And the important part right here is that the cell has access to the grid that it's part of, so it's a bit more like self-sustained, self-sufficient. And the other important thing is, since I would also want to offer the other way around, that whatever is the actual like value in the cell can have access to the cell that it is part of, optionally, if it wants to make use of that. Such that, for instance, you could say, hey, if I have a reference to the value like in the cell, give me my adjacent cells, for instance, right here, which you can obviously only do if you know you in the sense of the object that you're in, that it's in the cell, if you have a reference back to the cell. And the nice way to do this is inversion of control, of course. So the way that I did this here is that instead of passing, and this would obviously be the logical thing to do here, we say val value is t, right? Such that we have just yeah, the value in the cell, but then the value has like no reference back to the cell. Instead, what we do is we only give the value constructor that accepts a cell of the same generic type, and this constructor then returns this value. But the idea, of course, is that you only give it these constructors such that when actually this is invoked, you pass in, and that's precisely what happens here, yourself. So we pass this, so the cell itself, into the constructor, such that whatever is on the other side, if it wants to, it can save the reference to the cell and then return the value that we want to construct. And then we still have our value right here, and actually you see this is not a val, so we throw away the constructor right after. This is the whole idea of what's happening here. And with this knowledge in mind, this actually makes a lot more sense now. So what we do here, this looks a bit funky, but what all that's happening is that for each of the coordinates, we say created me a map from coordinate to one of these constructors for a value. So I figured the most obvious choice to say, okay, is a coordinate in the grid marked or not is a boolean, so this would be true, and a dot unmarked would be false, such that what we simply do is we create a bunch of lambda expressions with that accept a cell and return true or false, given if they are a coordinate that appears in our input or not. Right? So we know that for the coordinates, they do appear, otherwise you would have not parsed them. So we just say associate them with a lambda that returns true. We do not need the cell reference in this case, so we can just do it like this. The correct notation, of course, of this would be something like that. So we say we receive a cell and return true. Usually you would probably do like value, and we pass in the cell such that we then have the reference. In this case, we don't need that, it's just true. And then you see IntelliJ will tell us, hey, cell is never used, rename it to underscore or just get rid of it. So this will just be now all the coordinates to these lambda expressions right here. The only reason why I did this really is such that I can reuse my grid, since yeah, it is already doing what a grid is supposed to do in terms of data structure. So I figured, why not reuse it? Then the other thing is that you need, that's what I added right here, a new constructor for it, because by default what this grid only took is like all of the coordinates like exhaustively. So it's, you see it's a list of lists, so it's just like the matrix with the nested lists. But there's obviously a use case the other way around, such that you only have some of the coordinates you know the value for, and for the others you want to have a default value, right? Which is precisely what I have for this secondary constructor here. So we give it all the ones that we know are there, and for all of the other ones, we provide a default one such that if we reach, like, so if we would construct this thing, we would check, hey, do we have a value for 0, 0? No. So we invoke default. Do we have a value for 0, 1? No, 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 no. And then for 3, 0, 3, we check in the map, oh yeah, we do have a value. So let's use the value constructor of this one, such that there's whatever this is. In this way, it can stay generic, so we can still use booleans. That's, but we could also use any other value. So what we then just do is precisely what I described. We find the maximum x and the maximum y coordinate in our coordinates that we have here in this map, and of course we need to add one for the case that like everywhere on the corners here there's not a coordinate that we know about, in which case this thing might not be complete. Then we create like our outer lists with the max y and the inner with the max x, and then as I said, we look up every time, hey, do we have a coordinate for these x and y ones? If yes, yeah, get that constructor. Otherwise, we use the default constructor here nicely with the Elvis operator. And then in the end, we have the same data type as this thing usually takes. And then we can just call the regular constructor. That's the idea of this setup right here. The rest of the grid is not really important to know about, really. Yeah, we have the matrix internally that actually holds the cells. But we'll look at that in a second. So this is what is going on here. Obviously, default constructor, same method or lambda signature, but it just always returns false, right? Because we know if we do not have a coordinate for a x and y pair, then there's no marking, thus false. Right, now the only thing we really need to do is yeah, execute our fold instructions. And for the first part, we only need to fold the first one. Therefore, what I did here, there's an extra argument, fold first and only. It is optional. So if you do not provide it, as you see right here, we just take everything essentially. This is maybe a bit stupid, but at least then you can, it can stay like nice in one line. Otherwise, you can provide a number here, and then we take only the first n instructions and only fold those. Naturally then, for part 1, we say fold first and only 1, because we only want to fold or like execute the first one. Yeah, and then actually what we can do is, funnily enough, a fold operation. So in essence, what happens here is nothing else that we, for each instruction, we take the grid that we have and reduce it a bit further, or like we manipulate it to be another grid, right? We halve it in size, or maybe not even half it. We might be folding it somewhere else, but we change the grid in some way, and then we want to reuse whatever's the output from the previous iteration in the next one. Of course, you could do like a loop and override some stuff all the time, but yeah, that's not very idiomatic Kotlin, so fold is perfect here, and funnily enough also matches the theme of this puzzle. So we start obviously with our grid as the the starting point, and then for each operation we simply do with our current accumulator, so the current grid from the previous iteration, so to say, we just say fold it over with the current fold instruction, which is what we're iterating over. And so let's look at fold over, what that is doing. So the nice thing, of course, here is that this can use extension functions such that we can only offer this for a grid of Boolean. So any other grid of t, I don't know, a grid of int, would not have this function because there's no logical way to fold that over. So we only offer this now for grids of Booleans, which is, in my opinion, a perfect use case for an extension function, because then we don't need to clutter the namespace here of the regular grid. And actually in this specific case, we don't really have a use case even for a generic t, like any value in the cells that we could fold over. There's like no logical mapping there, so it doesn't even make sense to have it here in the first place. Whereas, for instance, get adjacent you can do perfectly generically, like to get the adjacent cells from x and y coordinates. You don't need to care at all what actually is in the cells, right? That is entirely doesn't matter at all. So I think this is a perfect use case for an extension function, because this is specific to a grid of Boolean. So what we now need to just do is essentially do the same thing, but switch it up slightly depending on if we fold on the x or on the y axis. So what I did right here is that I have this when expression here that checks the axis, and if we're folding on the x axis, which means I'll show you right here, that we can more naturally, so folding on the x-axis would mean this. So this is essentially the natural folding, so to say, for the simple reason that this is how the data is laid out in, well, not in memory, but how it's laid out in the data structure, because it's a list of nested lists, right? So each row would be a nested list, and then each of the rows is one element in the outer list, such that if we want to fold here and we want to essentially find out, hey, which part from here has to go over here, we want to be like doing it in this axis essentially. We always want to do it on the x-axis, because this is how the elements in the nested lists are laid out, right? You don't want to be, I mean, you could, nothing stops you from that, but it's very annoying to write code that would fold like this, because then you would need to get the index of everything across all the lists, which would mean a lot more accesses, first of all, and secondly, it's just hard to read in my opinion. Of course that would work, but yeah, it's hard to read. So let's first go with the nice case, which is x, in which case we just say what we use to fold and return a new, so we always return a new immutable grid, so we don't mutate our other grid. Actually, we cannot even, it's not mutable. We get the matrix from our grid that we fold over currently, and this is the matrix that we will use this on, as well as, so what I'm just doing here is I create a pair to then immediately destructure it. Maybe not the nicest way to do it, but yeah, I don't know, it makes for very readable code. It of course means that you construct a pair and immediately garbage collect it, so that's not super nice, but they're also pretty cheap. And what we have here is essentially what we want to use to find the coordinates that we want to retain in our grid that we return here, but on that more in a second. So what this simply means is we give it x and y coordinates and we return coordinates. You might now ask, like, why the hell would we have like x and y to return coordinates when coordinates literally is just x and y? You can just pass it directly. You don't need like level of indirection with this lambda right here. True, but that will make it very generic for the not so nice part, which is the y-axis. So as I said, if we have to fold on the y-axis, we can't like nicely iterate here and then check the other side, because yeah, they're separate like lists and nested on different like levels, the elements that is in each of them. But what does work very nicely is to transpose this. So if you think of this as a matrix, I actually reused my transpose function from the first or second day or something that I wrote, which we use right here. So we have this matrix transpose that we can actually use. Just quickly, if you don't know what matrix transposition is, we make all the columns rows and vice versa, such that for this example right here, for instance, this would still be 0, 0, but instead of the nested lists going like this, they now go like this, like down. So 0, 1 in this matrix transposed would actually be here. So now we go like that's the first list, and then this is the second list, and so on, which will allow us, and that's why I'm doing that we now again can fold such as this would be an x-axis. You see, if you would rotate this by 90 degrees, which is essentially what the matrix transposition does, then this line is now again like going from top to bottom, just as here, and then we can again nicely fold with each of the nested lists and its elements, or their elements rather. So in the case that we have to fold on the x-axis, I do essentially the opposite from this one. I transpose the whole matrix, and this you'll see in a second, I do this the other way around. So we still receive x and y in the lambda here, but now I construct the coordinates with y and x. Simple reason for that obviously being that since we work later on a transposed matrix, all the coordinates will also be wrong way around. So everything that was a y coordinate is an x and the other way around. And therefore we have to do this, but you'll see how this is used in a moment. So what we then do, we now have the matrix we operate on and a way to construct the new coordinates. We iterate over everything, every row in the matrix. We can now be, this is then each index, and that's why I'm using mapped indexed, is now the y coordinate. So if we do it with this example, in essence, both of the cases are the same now since we do the transposition. So due to the fact that we here say matrix and not this dot matrix, this refers to this one. So either you operate on the regular one or on the transposed version of it, such that essentially the y, what used to be an x on your original one, but since you transposed it, it's now also a y. It's a bit mind-bending maybe, but bear with me. I think it makes a lot of sense in a second. So what happens then is, let's take this case here that is a bit easier to see visually. We map over the matrix, and you saw that the index is the y, which precisely is of course the index within the outer loop. So over all of these like lists themselves, all of the rows. Which of course then it makes sense that that's y. So this is y0, y1, y2, and so on. So that's our y right here. And then each row is just the list that we're currently looking at. So now the simple thing we have to do, so to say, is do the folding. For that, if you think about it, the only thing we really have to do is to try to find out from both sides of the fold which two indices will like lay on top of each other. So the easy thing, of course, to do this, or the easy way to do this, of course, is to start from here and then always count one up in each direction and pair them up, such that you would know if you fold here on this line, this index and this index are now a pair because they would overlap. Like if you imagine that's fold over, this and that now overlap, and this overlaps, and so on and so forth. It might be that you have some that that have no partner. In this example, it's nicely always in the middle, but later with the actual puzzle input, it might be that you fold like here. So it can actually be that you fold in a way that some don't have a partner, but that's very easy to take care of course. So to arrive at this, to like pair them up and then check the indices, I have this lines merged field on the fold instruction. So once you construct one, this is actually directly calculated because you can do it directly and keep it in memory already. So all we do right here is for our fold instruction, we iterate from 1 all the way up to whatever axis we're we're folding on, And then essentially this is the distance away from the axis. So we start with one distance away, that would be here. So now all we have to do is simply create pairs of the value minus the distance and the value plus the distance, such that we arrive precisely at this, that we have, so if we're at distance one away from the value, in negative side would be this one, and one in positive would be this one. And then due to the fact that we like have this range right here, we like go bigger and bigger all the time. So next iteration we say, give me 2 minus away from the fold, then we get this, and plus. So that's how you arrive at like pairing up the sides. So this is nicely already stored right here, all the pairs of the indices, and together with the axis, you know, how to fold it. So all we now have to do is that we get these pairs, and the important thing here is that at this point both of them are x coordinates essentially, right? If you, regardless if you transpose the matrix or not, we essentially fold as if it would be an x coordinate. This is precisely what we get rid of in this case right here, such that the actual folding can stay like generic. And then you know that the first part, since we first always look at the minus one, is the one that we want to retain. So the important bit here is of course that it says we always fold up and left, such that these are the ones that are retained. Therefore, the first element in these pairs is the one that stays like in the final grid. So you see we fold like this pile of the paper onto the other one, such as this is like, I cannot mark this nicely, but like the left side is the one that is retained. Therefore, the first element in the pair is also the one that is retained. That's precisely what I named this here. So again, we destructure it. We just map over all of the pairs. And each time we know, okay, the left one, so to say, is the one that we keep, and the right one's the one we discard. The thing that's nice about this is, of course, that we do not need to know anymore if we fold X or Y, because we precisely get rid of this precisely with this when clause, such that we know, firstly, this is always an X now, because if it wasn't an X yet, we transpose the matrix to make it an X. And secondly, it's essentially always left now. So this is the one we retain, this is the one we discard. And of course, I named it X to know this is the Y and the X. So all we do now is we create our new coordinates at the point that we now retained. So we use this constructor now. And here now becomes important, of course, that we have this flipped around version for the case that we actually fold at Y, such that later on when we have our final coordinates again, they match again the matrix, since we transposed it earlier. So yeah, we pass X and Y in here and get back some coordinates. So what these coordinates then are simply like in the final grid that is retained, where are these coordinates? So this would then be, let's say we are in the first row and we say, okay, then Y is 0, of course. And maybe we're at the second spot. So this would be Y0 and X1, such that we construct coordinates, well, with precisely that, Y0, X1. And then these would be that one. So out of all of these coordinates, you already see where this is going. We again later can use our regular constructor of the extra constructor of the grid to say, okay, at this coordinate now there is, I don't know, either a marking or no marking, true or false. And to find out if it's true or false, all we obviously have to do is to check at both the retained and the discarded one, what is the value there. So we just say, get me out of my current row, get me the retained one and the discarded one, and see if either of them are true. So simply do an or, Boolean or in the middle, since they do overlap. So in this case, actually, the first one would be false, since there's nothing here. But the matching one on the other side, which is this one, would be true. Therefore, it's false or true, which is true. So we know for this coordinate, the new value going forward into the new immutable grid version is going to be true. That's all we do here. So now we know the new value. The thing that's important here that I briefly touched upon earlier, we have to use get or null right here. And if this value is indeed nullable, just assume that it's false. that there's no marking, for the sole reason that if we fold somewhere that is not exactly in the middle, and we would get like out of bounds exceptions, such that we check the index or something that is not even like part of the grid, we just assume there's nothing there, right? That's not going to be anything there. So yeah, that is taken care of. And then we just return these key value pairs. Essentially, at these coordinates, we now have this value. Yeah, this is going to be, of course, nested. So we have, you see it here, list of pair coordinates and Boolean. Since we did this for each of the rows. So simply what we do now is to flatten it to get like all the coordinates and their values again. And then we do exactly the same that we did in the very beginning to even construct the graph in the first place. So the part, let me see, where is it? Here, where we got like all the coordinates and these these fake constructors, so to say. We do the same here. So we just say associate each of the coordinates as the map keys with these constructors. The important thing right here is that now we do need to care what the actual value is. So this is the part that we returned here, that we determined here. Since it does matter this time, of course, that if we determined for sure that somewhere there's nothing, now we also want to retain this information. So if we fold over two parts, like let's say this, and both were false, then we want to retain the information. Okay, there's false there now, because we know for a fact that it will be false. Yeah, and then once we have this, you see actually it's the exact same data type as we used to construct the grid originally. This is exactly the same. So we again pass it to our grid constructor, the secondary one, and we would get a new grid. And then since we're doing this in a fold, this will then be the new accumulator for the next instruction. And we just do this over and over and over again, and the grid shrinks and shrinks and shrinks in size. And at some point, of course, we were done. We looked at all the instructions, and we can return our final grid. Of course, in this first part, we only look at the first one, so it only folds literally once, but that's the general idea. And as you can see, it would already support folding multiple times. Yeah, I think that's it for part one. So if you run this, then you would we simply want to know how many marked dots are there. So all we do is now we get all the cells of our grid and we count how many of them are true. So it is the cell, of course, and then the value, as you remember, is like the actual generic t, in our case a Boolean, since we know that we have a grid of Boolean, and then we check if it's true. So this would be like this, right? If value is true, but then IntelliJ says, hey, you can just do this. Fair enough. Yeah, so that's part one of day 13. Let's move on to part two, I'd say. So again, if you know it already, use the chapters below to skip ahead, although this is very quickly explained. Well, explained quickly, understood maybe not so easily. At least for me, it took like a moment, like what the hell do they want here from me? So the idea of the second part is that we now just execute all of the fold instruction we're given. So you see in the actual ones you receive, it's a lot more. You fold quite often. And it then says, the manual says the code is always 8 capital letters. And I was like, what the hell, what letters now? Where the hell did they come from? But then I read everything again, and it turns out that why you fold this is that at the end, like once you fold it over here, please enter the code found on page 1 of the manual. So you are literally supposed to like fold it, and then it will show a code after having folded it. So you must imagine that if you do this like you do here with the square, so you could imagine this maybe looks a bit like an O, right? If you do this with a way larger grid, you might actually get some letters in the end. So you might get O, X, or whatever, some letters, and that is literally the code. So you have to run all the folding instructions, so code doesn't change at all, and then read the thing. So yeah, the code doesn't have to change. We do the same. The only difference is here this time we don't say only fold the first one, but nothing, which is that we just fold everything. We take everything and do execute all the fold instructions. And then we have our folded grid. Now we need to print it somehow, right? So also what I did then, again, I thought, okay, extension function alarm, because it's a nice use case to only have on a grid of Boolean. Of course, in general, it would be nice to have like a good toString method on the generic grid, but there is not really a good way that you can print it, because depending on the toStrings of the values, you might get like some really messed up looking like visual representation of the grid. So I figured this is not really a good toString method. So instead I called it toPrettyString, which is, yeah, essentially it's this difference you have in Python between, I guess, wrapper and what's the other one called? Yeah, str or something. So like one is like a developer version of the toString, and the other one is the one you want to show to the user, I guess, or something like that. So this would be the toPrettyString, and toString shouldn't show like a visual form of the grid, in my opinion, because yeah, it's a bit overkill. Yeah, but then again, I figured a good thing for an extension function, because for a generic grid, I wouldn't know how to nicely print this prettily. So for now, we can only support it on a Boolean grid. So this is perfect to do it like that again, just as above here with the fold over. This you can do very nicely with yeah, Kotlin, very idiomatically. All we have to do is we take the matrix, we join each of the rows so this is join by string. Join to string is doing a map essentially in the background, and then executes this lambda and then concatenates everything together with this separator. So if we go over the rows and concatenate whatever is the return type of this, the return value of this, with a new line character, we obviously automatically get like, yeah, the grid. So like this, if we do the first row and then add a new line, we automatically get like nicely, yeah, a visual representation of the grid. And then within everything, we join by nothing, empty string. And we simply say if cell value is true, then we take this blocky UTF character right here. And if it's false, we take this one that is a bit like more transparent, such that you get exactly what you see right here, just in a bit nicer looking. So instead of using pound signs and dots, which is a bit hard to, the contrast is not very good, I use these blocky ones such that it will also be more uniform, right? Because these ones have different heights, and it just looks messed up. And then yeah, with this very short code, you get like a very nice visual representation of the grid. Right, so if we run this, actually, let's do it right now, you will get the following result. And then we're already done with part 2. I very much like this part 2 since it's quite different. So if we run this takes a moment, we get this yeah, very visual output, and you can actually now read the letters. So it's RCPLAKHL in my case, obviously different for your input. So you literally have to read this. In this case, of course, I just went ahead and entered here, and that was it. I've seen people like OCR this, like try to machine computer vision read what the letters say there. Pretty nice. Obviously a bit overkill. But yeah, that's part 2 as well of day 13. If you enjoyed this, consider subscribing to the channel. If there's any questions that you still have, either you can drop me a comment, or there's also a Discord community server, which you can find in the description of this video, that you can join and we can chat, or you can also ask more questions. Yeah, that's it for day 13. I see you on day 14. Tschüss.